KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
That is work power energy 1. This is the second class. In this class we are going to discuss one example problem to find the angle between two vectors, and then we are going to discuss work energy theorem, which is very important for us regarding board point of view, and the formula is very important for us regarding competitive exams like NEET and JEE mains, right. So in our last class we focused on how can we define the work, energy and power. Just we discussed that how can we define, not the complete definitions, right. So there is a correlation between the physical definitions and the physiological pictures, okay, that we raised and that we discussed. Afterwards we also discussed about the scalar product, right. So in case of scalar product, how we will multiply two vectors. Already you know that two vectors you can multiply in two ways. One is vector product or cross product, another one is scalar product or dot product, right. So a vector product we already discussed in the chapter of motion in a plane, but now last class we focused on scalar product by taking two vectors A and B. How can we get the scalar product? That is a scalar quantity, and scalar product obeys that is what the commutative law and distributive law also, right. And what about the unit vectors? And by taking two vectors A and B, A is like Ax into I cap plus Ay into j cap plus Az into k cap, B is like Bx into I cap plus By into j cap plus Bz into k cap. In that manner we also found what is A bar dot B bar, right. Okay. So in this class we are going to focus on one example problem, and afterwards work energy theorem, okay, right. So here first we will go through the example problem. You just focus here. First I will read the problem. See here, find the angle between force capital F is equal to 3i plus 4j minus 5k unit and displacement d is equal to 5i cap plus 4j cap plus 3k cap unit, okay, full stop. Also find the projection of F on D. Right, okay. So in this problem, if you observe carefully, he is asking to find the angle between two vectors. One is F vector, another one is D vector, right. So here D is the displacement vector, F is the force vector, right. And here I already told you, we already discussed in the last class, I cap, j cap, k cap are the unit vectors along x axis, y axis and z axis. Here also the same thing, I cap, j cap and k cap are the unit vectors along x axis, y axis and z axis. If you observe carefully here, it is a 3-dimensional, right, and it is also 3-dimensional because all are present, no, I cap, j cap and k cap, right. Here this is also, right. So what is our interest in this problem? We are going to find the angle between force and displacement, okay, right. According to the scalar product, what we discussed in our previous class, f dot d is equal to fx into dx, right, plus fy into dy plus fz into dz, okay, right, fx into dx plus fy into dy plus fz into dz. So here it is plus ma. F dot d is equal to fx into dx plus fy into dy plus fz into dz. That is equal to, right. So see that ma, fx into dx, see this is, it is 3 into 5 plus fy into dy plus it is what, minus 5 is the fz, it is dz into 3, right. So 3 into 5 plus 4 into 4 plus minus 5 into 3 will give you 16 unit. It is 15 ma, it is plus 16 and it is minus 15, right. So it is plus 15, it is minus 15 will get cancelled and the result will be 16 unit, okay, right. So this is the resultant of, this is the result of dot product of two vectors. One is force vector, another one is displacement vector, okay. Hence afterwards, you know this, it is the definition of scalar product. From the definition of scalar product, we can write it as f bar dot d bar, otherwise f dot d, because both are vectors only, no, right. So the notation of vectors we discussed in the chapter of motion in a plane, right. Just by writing thick letters, otherwise by writing light letters and keeping a vector symbol on the top of the physical quantity symbol notation, then it will be treated as a vector quantity, right. So here I am saying in words also, please keep in mind force is a vector and displacement is also a vector, okay, right. So f bar dot d bar is equal to fd cos theta, that is equal to 16 units already we found, see here, right, okay. So fd cos theta is equal to 16 unit. Then what about cos theta? Generally cos theta is equal to f bar dot d bar divided by fd, am I right? Okay, right. So f bar dot d bar by fd, f bar dot d bar already we found it is 16 units, then divided by f into d, no, right. So what is f? What is f? Square root of fx square plus fy square plus fz square. What is d? Square root of dx square plus dy square plus dz square, okay, here, right. So here we have to write the magnitude of f and the magnitude of d, magnitude of f and magnitude of d, right, okay. So basically we have to write here f and here we have to write d. Not in vector form, I have to write the scalar form because you have to write the magnitude. See this, there is difference between these two and these two, right. So here it is a vector, it is also a vector, okay, but when we multiply these two we are getting this result, right, okay. So 16 divided by modulus of f will give us square root of 50, otherwise we just take it as square root of, see, square root of 3 square plus 4 square plus minus 5 square. Then what will happen? 3 square means 9, no, 4 square means 16, no, 5 square means minus 5 whole square will give you 25. Then 9 plus 16 plus 25 will give you square root of 50 into, here what is that? It is a modulus of d, right. So here also what is this? This is the d vector, right. So square root of 5 square plus 4 square plus 3 square, 25 plus 16 plus 9, it will be square root of 50, right, okay. Next 16 divided by square root of 50 into square root of 50 means 50 will come, right, okay. Now it will give us 0.32, 2 8 and 2 25, okay, right. So finally we will get it as 0.32, 0.32, okay. Then theta, cos theta is equal to 0.32, no, theta is what? Theta is equal to cos inverse of 0.32, cos inverse of 0.32, okay, right. So now we found the angle, between the two vectors f and d, that is cos inverse of 0.32. But he is asking one more thing, find the projection of f on d, find the projection of f on d. It is very simple, Actually, this we discussed in our previous class how to find f on d, d on f, etc. by taking a on b, b on a, like that. Okay, right. But here in this problem, he is asking to find projection of f on d. Projection of f on d means here we have to find f cos theta. F already we know, right? It is what square root of 50 and cos theta is equal to 0.32, right? So f cos theta is the projection of f on d according to this problem. Okay, right. Now next continuation topic in our class or in this class, that is notions of work and kinetic energy. Notions of work and kinetic energy, right? And the work energy theorem also, right? Notions of work and kinetic energy and work energy theorem also, right? So now we are going to discuss work energy theorem. Okay, right. So in our chapter, that is what motion in a straight line, we discussed equations of motion. There are 4 equations of motion. V is equal to u plus at, s is equal to ut plus half at square, v square minus u square is equal to 2as, Sn is equal to u plus a into n minus half. So these are the 4 equations of motion we learned from motion in a straight line chapter. Okay. So there itself, what is the third equation of motion, which is v square minus u square is equal to 2as. Okay. So this is the equation of rectilinear motion under constant acceleration a. Under constant acceleration a. Okay, right. V is the final velocity, u is the initial velocity, s is the displacement. S is the displacement. Okay, right. After that, it is equation number 1 ma. It is equation number 1. Okay, right. Now this equation v square minus u square is equal to as, we are multiplying with m by 2 on both the sides. See this, multiplying the above equation with m by 2, we have, what we have, see here, m by 2 into v square minus m by 2 into u square is equal to 2as into m by 2, right? So here 2 will get cancelled, no? So what is this? MAS. This is MAS. MA means it is f tau, right? That is equal to f into s. That is equal to f into s. Okay. Half mv square minus half mu square is equal to f into s. It is equation number 2. It is equation number 2. So this is the equation number 1, which is equation number 2. We can write like this now. You just cross check yourself. Half mv square minus half mu square is equal to f into s. Okay, right. So the above equation, right? The above equation follows from Newton's second law of motion. The above equation follows from Newton's second law of motion. We can generalize to 3 dimensions by using the concept of vectors. By using the concept of vectors. Okay, right. Here itself, this equation which follows Newton's second law of motion means that you know very well, ma. What is the Newton's second law of motion? The rate of change of momentum. The external force acting on a body, right? The external force acting on a body is directly proportional to the rate of change of momentum. You can see this picture, right? Okay. It is the horizontal surface on which there is a body of certain mass m, and when the external force is going to apply, just when the force is applying, its velocity is u. After that, by covering the displacement d, its velocity will be increased or its velocity will become v. Okay. So this is this is the situation. According to the situation, you can say that whatever the external force applying on the body causes to increase its speed. To increase its speed, meanwhile it is going to cover certain displacement, right? So whenever it is going to increase its speed, automatically the kinetic energy is said to be increased. So initial kinetic energy is 1 by 2 mu square and final kinetic energy is 1 by 2 mv square. The change in kinetic energy is 1 by 2 mv square minus 1 by 2 mu square, that is equal to ma into s, that is equal to f into s. Okay, it is the equation number 2. Next, say this. The above equation follows from Newton's second law. Okay, right. Generalizing for 3 dimensions, right? So the same equation we are going to write in 3 dimensions. See this, ma. V square minus u square is equal to 2 into a dot d, right? It is the acceleration vector and it is the displacement vector. Acceleration vector and displacement vector, right? So this is also going to multiply with m by 2 on both the sides. Then what will happen? As usual, as we did just now, because when we are multiplying with scalar, the process is same, right? When you multiply with vector and another vector means the problem comes, because you can multiply vector in 2 ways. I already told you, right? So here just we are multiplying with m by 2. You know very well, mass is a scalar quantity which has only magnitude but no specific direction. Okay, right. So multiplying with m by 2 on both the sides, then see here 1 by 2 mv square minus 1 by 2 mu square is equal to, here we are multiplying with m by 2, no? So already 2 is there, ma. So already we are multiplying, we are going to multiply with m by 2. So 2 will get cancelled. Finally m into a bar dot d bar, right? So ma is equal to f, no? So you can write it as f bar dot d bar. So it is the force and it is the displacement, right? So this is the vector form. This is the, that is what kinetic energy, work energy theorem, work and kinetic energy relation, work energy theorem in 3 dimensions, because here it is a scalar quantity. Kinetic energy is a scalar quantity, and whether it is initial kinetic energy or final kinetic energy, whatever it may be, kinetic energy is a scalar quantity, right? And by multiplying 2 given vectors, that is what the scalar product. If you multiply 2 vectors, otherwise the scalar product of 2 vectors gives a scalar quantity, right? That is half mv square minus half mv square is equal to f bar dot d bar. That you can write like this, ma. Kf minus ki is equal to w. Kf minus ki is equal to w, right? So when kf minus ki is equal to w, it is what? Final kinetic energy of the object or body. It is the initial kinetic energy of the object or body. So that is equal to w. That is equal to w. Kf minus ki is equal to w, right? Okay. So that is simply said to be work energy theorem. Work energy theorem. Okay, right. Next, work is done by a force on the body over a certain displacement. I will repeat once again. Work is done by a force on the body over a certain displacement. Okay, right. Next, the change in kinetic energy, the change in kinetic energy of a particle is equal to the work done on it by the net force. The change in kinetic energy of a particle is equal to the work done on it by the net force, right? So the net force or the external force. So the resultant force acting on the body, the resultant force acting on the body is equal to the change in kinetic energy of a particle or object or body, whatever it may be. We are taking based on the situation. Okay, right. So this is the work energy theorem, right, in 3 dimensions or in vector form. Otherwise, generally initially we did in the general thing, that is what half mv square minus half mv square is equal to f into s. Okay, right. But the same work energy theorem, the same work energy theorem we can also do in some other manner, right? You just focus here, ma. I will tell you, right, as simple as such. I will explain you. See here, this picture I already explained you, but based on that picture, right? So general linear method, you can say that a linear method, otherwise the conceptual method. Okay, because here we are using the definition of work, the definition of work, right? So I already told you in last class also, because in some situations we need the definition, but clearly we are going to discuss in the next class, right? Here work is said to be done. Work is said to be done when a body displaced along the direction of applied force. Work is said to be done when a body displaced along the direction of applied force. Okay. At the same time, you also keep in mind work is equal to force into displacement. Force is a vector quantity and displacement is also a vector quantity, is a dot product of two vectors, force and displacement. Okay. It is from definition, right? So mathematically work is the product of scalar product of force and displacement vectors. I will repeat once again. I already told you one definition, that is what work is said to be done when a body displaced along the direction of applied force. Okay. But after that I also need to say work is the scalar product of two vectors, that is force vector and displacement vector, okay ma, right, that is equal to ma into d, because F is equal to ma into d, no, force is the product of mass and acceleration, right, okay, and m into what is a, this is what, when a body is moving along a straight line, that is what in case of translatory motion or rectilinear motion, the third equation of motion, that is v square minus u square is equal to 2as, v square minus u square is equal to 2as, okay. Then what is the a is equal to v square minus u square by 2s. So that s here they are using a d, that is they are using d, right. So v square minus u square by 2d into d will get cancelled, no. Then what will happen? 1 by 2 mv square minus 1 mu square, right. See here, work done by the external force causes the change in kinetic energy of the body. Work done by the external force. Here you can write resultant force also. Here you can write the net force also, because already we know from the chapter of laws of motion, whenever the force, external force is acting on a body, right, the frictional force also starts to act, right, and the gravitational force and the normal force will cancel each other, right. So that's why we have to write it is a resultant force. For seeing it is external force, but finally the resultant of all the forces acting on a body is the main point which causes the change in kinetic energy of the body. So at last you can write work done by the external force causes the change in kinetic energy of the body, right. So the body initially it has u velocity, and when you are applying some force, its velocity increased from u to v, meanwhile it is going to cover the displacement d, okay. So it is a work energy theorem, right. Here itself you have to keep you have to observe one of the important point, that is initially the body, just while applying some force, it has some velocity, that is 0, right, while applying the velocity it has some velocity, that is u, not 0 ma, it is u, it is the initial velocity, right, okay. Now he is going to apply some force. The resultant force acts on the body, causes the increasing in kinetic energy, right. So what will happen there itself? Certain amount of work is going to done. Who is doing the work? Who done the work? So this force is going to do the work, right. So finally we are taking and we are saying that work is the product of force and displacement. That is equal to change in kinetic energy. You know very well from our lower classes onwards, kinetic energy is the energy possessed by a body due to its virtual motion. Kinetic energy is the energy possessed by a body due to its virtual motion, right. So here when its velocity, the formula for kinetic energy is half into 1 by 2 into mass into velocity square, right. So in our coming classes we are also going to know the derivation for kinetic energy, that is how it is equal to 1 by 2 mv square, okay. But here it is not the topic, but anyhow I need to say Okay, what is kinetic energy? I need to say, because of using this kinetic energy always, first we have to know what is kinetic energy. No, that is okay. So kinetic energy is the energy possessed by a body due to virtual motion, right? Due to its virtual motion. Okay, right. So here the amount of work done is equal to the change in kinetic energy. That is the only kinetic energy theorem. Please try to understand the logic behind the work kinetic energy theorem, otherwise work energy theorem, because kinetic energy is also energy only, no? So as simple as such, it is work energy theorem. So already body is moving with some velocity. When you apply certain amount of force, its velocity will be increased, so that certain amount of work will be done. So that whatever the work is going to done, that will be converted in the form of kinetic energy. It will be converted in the form of kinetic energy. That is simply said to be work energy theorem. So my sincere request in this topic, is please try to understand, please try to observe. If you apply certain amount of external force, what are the things to be happened? So I am saying that the displacement is going to take place. I am saying that the velocity is going to increase, or speed is going to increase. I am saying that the kinetic energy will be increased. Finally, I am saying that the work is said to be done. So please try to understand the relation between the resultant force and the displacement and the kinetic energy and the work. So all quantities are important. Every quantity has its own importance in this case, right? So that is the thing. Okay, ma? Right. So in this class, we discussed one example problem. There we find the angle between two given vectors. Afterwards, we discussed what is the work energy theorem. Okay, right. So in our coming class, we will continue with next continued topic. Thank you.